Hey guys, so far in our adventures with the binomial expansion, we've had a look at expanding 1 plus x to the power of n and also 1 plus ax to the power of n. Now there hasn't really been much context as to why we would do these. So we can use binomial expansions to approximate certain numbers raised to a power. In particular, this is really useful for decimals to a certain power. So, for example, let's say we wanted an approximation of 1.02 to the power of 7. Well, how we could do that, we could expand 1 plus x to the power of 7 and then set x equal to 0.02. So if we were to expand 1 plus x to the power of 7, we would then, do all that and then set x equal to 0.02. Now, up to here as well, you've probably noticed we've been writing our answers in ascending powers of x, and sometimes when we have large powers, we've only written down maybe the first 4 or 5 terms. Now the reason for this is, when we're approximating these guys, as our power of x gets bigger and bigger, then the values when x is a decimal get really, really small. So we don't really have to worry about them because they are not going to make much difference to the answer. So here, for example, when x is 0.02, even x to the power of 4 is going to be ridiculously small. That's 0.02 times 0.02 times 0.02 times 0.02. So we can quite happily ignore higher powered terms of x when we are using approximations. So let's actually go ahead and do this guy. Okay, so for part A we want to expand 1 plus x to the power of 7, giving the first 4 terms in ascending powers of x. So, well, let's do this. We've been doing this a lot now. So we are going to get 1 plus x to the power of 7. Well, it's going to be 1 plus 7 choose 1 x plus 7 choose 2 x squared plus 7 choose 3 x cubed. So if we now get those coefficients normally, we would have 1 plus 7x plus 21x squared plus 35x cubed. So there's our expansion to 4 places over the first 4 terms in ascending powers of x. Okay, then for part B, then we want to use our answer to part A to approximate 1.02 to the power of 7. So here in purple is our answer to part A. Now, really, when we cut off terms, we should now use this little wavy equals sign, which we read as is approximately equal to. So we now know from part A, 1 plus x to the power of 7 is approximately equal to 1 plus 7x plus 21x squared plus 35x cubed. So how does that help us here? Well, we want to expand, or we want to approximate 1.02 to the power of 7. We know approximately what 1 plus x to the power of 7 is. So what we do now then, we need to find what value of x to substitute in to the approximation. So in other words, we want the stuff inside of the brackets. So we want 1 plus x to equal 1.02. So 1 plus x we want to be 1.02. So if we solve that for x, we simply take away 1. So we would get x is 0.02. So we now substitute that into our approximation. So this x equals 0.02 gets substituted into the approximation of our expansion. So we are going to get then 1.02 to the power of 7 is approximately equal to 1 plus 7 lots of 0.02 plus 21 lots of 0.02 squared plus 35 lots of 0.02 cubed. So if we now use a calculator to work that out, we will get that 1.02 to the power of 7 is approximately equal to 1.14868. Now if we compare that to a calculator answer, we can see it's pretty much accurate, at least to 4 decimal places. So here we go, 1.148685. So really that 8 would round up to a 9. Now, you might ask, what's the point in doing this if we've just got to use a calculator to get the approximation? To which I completely agree, but we need to be able to do it because our exam papers will ask us to do it. Okay, let's do some more. Okay, example 2, we want first of all then find the first 4 terms of 1 minus 3x to the power of 10 in ascending powers of x. So, this is a slightly trickier expansion where we have a coefficient on the x. So, we're going to get 1 plus 10 choose 1 times minus 3x plus 10 choose 2 times minus 3x all squared, and then plus 10 choose 3 lots of minus 3x all cubed. Okay, so let's write that out a bit nicer. So we've got 1 plus, well, 10 choose 1 is 10 times minus 3x. It's going to give us minus 30x. 10 choose 2 is 45. So we've got 45 times minus 3x all squared. Minus 3x squared is going to give us positive 9x squared. 9 times 45 is 405x squared. And then our final term is going to be, well, 10 choose 3 is 120. minus 3x cubed is minus 27x cubed. So 120 times minus 27 is minus 3240x cubed. So there are the first four terms of that expansion. And for part B, we want to use our answer to part A to approximate 0.97 to the power of 10. So, we now know that 1 minus 3x to the power of 10 is approximately 1 minus 30x plus 405x squared minus 3240x cubed. So, we need to work out what value of x to substitute into that. So, for that, again, we need to, well, we're trying to work out 0.97 to the power of 10. We've got an expression for 1 minus 3x to the power of 10. So we want the stuff inside of the bracket, we want this to equal 0.97. So, all we do is we set 1 minus 3x equal to 0.97, and then from that, we solve that for x. So, if we add 3x, we get 1 equals 3x, add 0.97, take away 0.97, 0.03 is equal to 3x. Therefore, x is equal to 0.01. So we now substitute that value of x into the approximation of our expansion. So x equals 0.01 gets substituted into this expression here. So we are going to get 0.97 to the 10 is approximately equal to 1 minus 30 lots of 0.01 plus 405 lots of 0.01 squared minus 3240 lots of 0.01 cubed. So if we work that in our calculator, see what we get for our approximation. Okay, so we get our approximation of 0.97 to the power of 10 to be approximately 0.73726. Now if we look at the exact or the calculator value, you can see this approximation is less accurate than the one we did in the first question. So this is only accurate up to 3 decimal places. So the calculator says 0.7374. So our approximation is only accurate up to the 3rd decimal place. Now let's think about why that might be. In this one, we expanded 0.97 to the power of 10. In the first one, we were only expanding to the power of 7. So, we were raising this guy to a higher power, but we used the same number of terms in our expansion. So, really, we can only expect it to be less accurate. Okay, let's do one more. Okay, for our last example then, we're going to look at one involving fractions. So again, we want to find the first four terms of 1 minus x over 4 to the power of 9 in ascending powers of x. So, be very careful here, we have a negative fraction. So, using the formula, we're going to have 1 minus, 1 plus 9, choose 1, lots of minus x over 4, plus 9, choose 2, times minus x over 4 squared, plus 9, choose 3, times minus x over 4 cubed. So, if we sharpen that up, we've got 1, and then we got 1. 9 choose 1 is 9, so we got minus 9x over 4. And our third term is going to be, 9 choose 2 is 36, minus x over 4, all squared, is positive x squared over 16, so we get 36 x squared over 16, which has a common factor of 4, so that's going to cancel down to plus 9x squared over 4, and then our final term, 9 choose 3 is 84, minus x over 4 cubed is minus x cubed over 64, so there's a common factor of 4 between 84 and 64, so if we divide that away, we are going to get 84 divided by 4 is 21, so minus 21 x cubed over 64 divided by 4, which is 16. So there's our expansion, or the first four terms of our expansion of 1 minus x over 4 to the power of 9. Again, and finally we want to use our answer to part A to approximate 0.999 to the power of 9. So, we have an expansion, or an approximation of an expansion. This should be wavy brackets. So we have an approximation to the expansion of 1 minus x over 4 to the power of 9. So we set 1 minus x over 4 equal to 0.999. If we add x over 4, we get 1 equals x over 4 plus 0.999. Take away the 0.999, we get 0.001 is x over 4. Therefore, x is 0.004. So, now the mission is just to substitute that value of x into the really lovely expansion up there. Do that, make sure that you get. So, for our approximation, we should get 0.999 to the power of 9 is approximately 0.99 35916. which, if we compare that to a calculator answer, that is actually incredibly accurate. So we get 0.9910359116 on a calculator as well. So it's accurate up to that decimal place. Now, one reason that might be more accurate is that we've got a much smaller decimal value for x. So that's going to home in it a lot more accurately. Okay guys, hope you found this useful. Personally, I dislike it because you have to use a calculator. So, thank God that's over. See you in the next one.